Okay, this is going to walk through ionic names and formulas. If you have been in class, you've done these 10, you've come up with the names for them, but I'm going to go over them real quick. But I'm also going to write the formulas given the names. Okay? First thing I'm going to do is take all these metals that are here and find them on the periodic table so we can zoom in and see which ones need Roman numerals and which ones don't. So we've got sodium, cobalt, lead, magnesium, okay, so watch this zoom in. Okay. I can tell that for lithium, sodium, magnesium, calcium, I am not going to need Roman numerals. They only form one kind of ion. Those are going to be simple. I can tell that for silver, same thing. Not going to need a Roman numeral. He only forms one kind of ion. However, for iron and cobalt and lead, those three I will need Roman numerals because they form more than one kind of positive ion. So there's lead 2 and lead 4. And if I name it, I'm going to need to know which one is used. There's iron 2 and iron 3. There's cobalt 2 and cobalt 3. So let's see. Iron, cobalt, and lead are the ones that need Roman numerals. And that is these guys. Iron. They need Roman numerals and nobody else does. So let's do the other ones first because it should be very straightforward. Magnesium and fluorine form magnesium fluoride. Okay. Down here, silver and nitrogen form silver nitride. Sodium and sulfur form sodium sulfide. Okay. Now going back up here to notice polyatomic ions. This is sodium. So these guys together must be my negative ion. My ionic compounds are only going to be made of 2 pieces, positive and negative. Positive ion, negative ion. So if this is sodium, this must be a polyatomic ion on table E. And here he is, hydroxide. Keep them together. They are a chunk. They are covalently. They're strongly bonded together. If I have him in a compound, it's either going to be 1 hydroxide or 2 or 3 hydroxides, but the oxygen and the hydrogen never shall separate. So, oops. Sodium hydroxide. Now, I'll point this out. This is one of the only polyatomic ions that has an IDE ending. Most of the time, an IDE ending tells you that it's just an element, and any other kind of ending, like ate or ite, is a different, Oh, cyanide also. Cyanide ends with IDE. Okay. Let's find the other polyatomics. This is straightforward lithium, so SO3 must be another one. Sulfite. This guy breaks here. Ca is calcium, so SO4 must be another one. Sulfate. And because this guy's in parentheses, it's easy for me to tell where the positive and negative ions are. It must be that this whole front guy is the positive ion, and then maybe this whole thing is the negative ion, and both of them can be found on table E. Ammonium phosphate. And you see this -3? And he's only +1, so hopefully it's obvious why there's a 3 outside the parentheses. Okay, now I left these guys for last because they're tricky. Why? Well, the metals can form more than one possible ion. So I'm actually going to work my way around here. FeO, iron oxide, right? But the question is, which iron? And it takes a little bit of detective work. Oxygen has a -2 charge, and iron could be +2 or +3. And I have to remember my goal. What's my goal? My goal is to name the compound FeO. So I think this one sort of solves itself, right? They are bonded in a 1-to-1 ratio. So if oxygen is a -2 ion oxide, the iron here has to be the 2. So this is iron 2 oxide. The Roman numeral tells me literally the charge on the iron. Iron 2 has a +2 charge. It may or may not show up in the formula. There's no 2's in this formula. It's because that's how the charges work out. Okay, now let's focus on this guy, CO3P2. Cobalt something phosphide. And the question is, what's the Roman numeral? So the only thing I have to solve now is what is the charge on the cobalt. So if I know this is my goal, CO3P2, and I go doing some detective work, maybe I can figure out the charge on the cobalt. Okay. The periodic table tells me that a cobalt ion could have a +2 or a +3 charge, and a phosphide ion has to have a -3 charge. There's some positive ones too, but I'm ignoring them because I already have a positive ion, and like charges would repel. So, process of elimination, I'm like noticing this +3 -3, because I'm noticing that if the cobalt 3 was used, they would just come together. But that is not the situation that I have. So I'm thinking that the cobalt 3 was not used. And I look at this and I say, okay, if the cobalt 2 was used, then these charges would cross down, because then I'd have 3 positive ions that are each +2 for a total positive charge of +6, and I'd have 2 anions that are each -3 for a total negative charge of -6. And that's why it works. And that is why, what was I trying to figure out here? Out of this whole investigation I did, all I really wanted to know was, what was the charge on the metal? 2. Very similar process for this guy. Pb is lead. And CO3, I can tell that's a larger guy. So I go looking for him on the polyatomic ions chart. Table E says he is carbonate. Lead something carbonate. Now, when I go looking into this and investigating, I need to know everything about that carbonate, especially his charge, because I need to know how he's going to bond to lead. Okay? I'll zoom out a little, give myself some room. Okay. Keep in mind our goal. Our goal is to properly name this guy, Pb CO3 2. CO3. Table E says carbonate has a -2 charge. 2 minus -2 doesn't matter. The periodic table says lead has a +2 or a +4. You know what, this is also easier by process of elimination. See this +2 and -2? If it was the lead 2, they would just smush together, right? If it was the lead 2. But that is not the compound I'm going for, so it must not be the lead 2. I like this. I like this process of elimination thing. Let's see what happens if we use lead 4. Okay. I could cross these, or you could just think it out, right? +4 -2. Don't I need 2 of him? If I had 2 of these carbonates, then I'd have a -4 to cancel out the +4. So that bit of logic can just get you to the answer. Or you can cross the charges, but you have to cross them and reduce them. You have to reduce this 2-to-4 ratio to a 1-to-2 ratio. And you end up with, ding, 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 our goal. And we did all of that to answer the question of, what's the Roman numeral on the lead? Boom, +4. +4 is what worked. So the Roman numeral on the lead is IV, 1 less than 5. Okay. Now, look at this, lead 4 carbonate. We already did it. CO3 2. Let's figure out these formulas. Sodium acetate. Now, this does not end in IDE. So maybe it's a polyatomic ion. Okay? So, I know sodium is a +1, but acetate is that or that. You'll notice they're actually the same. They both have 2 carbons, 3 hydrogens, 2 oxygens, and a -1 charge. So if I put them together, I love this situation. I love it when it works out like this, right? +1, -1, just smush them together. Okay? It looks much more complicated than it is because I just found acetate on table E and I made sure the charge is canceled. Okay, potassium chloride. Oh, that's too easy. Okay. Do notice the IDE ending? Like, oh, chloride, that's a normal IDE ending, so this is just the ion that chlorine forms. So, K +1, Cl -1. Oh, that's great. I love it when that works out. See how? Okay, I'm going to fold this so I have more room. The next one is manganese 2 bromide. Okay, now manganese is Mn. He has lots of possible positive charges, but boom, they have to tell me which one, because now this is the reverse of the situation. If I have a name, they have to tell me what the charge on the metal is if it's unclear. Okay, bromide, that's my normal IDE ending. So it's just bromine. Crisscross applesauce. Mn. Br2. Okay, cadmium nitrate. Ooh. Wow, okay. If you go looking for it, this is cadmium, Cd, with a positive 2 charge. But nitrate, that's a different ending. So we must be on table E, NO3 minus. Okay. The periodic table told me that cadmium has a +2 charge. Table E told me this about nitrate. Oh, they're so lazy they don't even put the 1 here, -1. Ooh, obviously I'm going to need 2 of this guy. I cannot mess with him at all, though. So, protect him with parentheses. Okay, the nitrate is in parentheses. Okay, copper 1 cyanide. Ooh, this guy, you might go looking for him for a while. Even though he has the IDE ending, he is a polyatomic ion on table E. Cyanide, Cn with a -1 charge. Copper 1. Copper with a +1 charge. It could have been copper 2, but it's not. It's copper 1. That works out nicely. Okay. Barium sulfate. Ooh, there's another ATE ending. Here's another one too, phosphate. I'm going to find these on table E. Nitrite, ITE ending. I'm going to find those on table E. And sulfide is just sulfur. Okay, barium sulfate. There's the sulfate, SO42 minus. A lot of flipping. There's the barium, +2. That works out. Okay. Nickel 3 phosphate. I don't even have to look. If I know what nickel is, if I know nickel is Ni, I don't even have to find him on the periodic table because they told me +3, nickel 3. Must be that there's a couple kinds of nickel. I want the one with the +3 charge. Boom, there's phosphate, PO4 3 minus. Oh, they're being very generous with these charges. Notice that the +3 and -3 cancel out. Nothing else is changed. NiPO4. I would not lose this 4. If I lost that 4, I would actually be losing 3 entire oxygens, right? And probably they'd take some of this charge with them. Okay. Chromium 3 sulfide. Now I've already said that IDE, that's the normal IDE ending, so that's probably just sulfur. So chromium 3 has to be chromium with the positive 3. Has to be. Sulfide is sulfur with a negative 2 charge. The positive charges will not be used. Okay, now, plus 3 minus 2 do not cancel out. So I have to do crisscross applesauce with the ratio for Cr2, S3, zinc nitrite, ITE ending. I'm going to find him on table E. Meanwhile, here's zinc, Zn positive 2. Nitrite. I think nitrite is NO2 with a minus 1, but I should show you. Nitrite, NO2 with a minus 1. And they don't even write the 1, minus 1. I need 2 of these guys, right? He is a big guy. I can't mess with any. Imagine, put him in parentheses. NO2, he is a chunk. So if I want to cross these charges, I can't touch anything inside there. But I can take this 2-to-1 ratio and flip it and say my 2-to-1 ratio of charge has to become a 1-to-2 ratio of ions. Lost my black pen. Let's see. Zn. NO2, 2. Ding, ding, ding. All ionic compounds are empirical formulas, which is simplified. Now, that doesn't mean you would ever simplify any of the subscripts that are in the polyatomic ions, but just between the ions, the ratio of ions. Like for the zinc nitrite, a 1-to-2 ratio works. A 2-to-4 ratio works. A 6-to-12 ratio works. But we go with the simplest ones because these are all crystals. They're all these like salt-like compounds that grow into however big a crystal they want to be. So this could be Zn 1 million, nitrite 2 million. Doesn't make sense to make it depend on the size of the crystal. Okay, hope this helped.